So whenever I say power circuits, machine power circuits, y'all know exactly what I'm referring to? No? That's okay. So draw a little picture over here. Going back to our motor control days. Y'all remember seeing stuff like this in your lab manual? So this portion of the circuit down here, this is what we primarily were wiring up in motor controls, right? What do we call this type of circuit down here?
One line diagram?
It's not a one line. It is a ladder diagram, right? But what kind of circuitry is that? Controls, right? This is, I know I just drew like a light switch and a light, but this is where you have like all your push buttons, the coils, right? All your little lights, every timers, relays, whatever you need in your circuit. That's all for the control portion, right? But then we have this circuit up here that's going to our motor, this three-phase circuit. So even in motor controls, you have the three-phase circuit, your three phases. But what was this circuit up here called? Power circuits, right? So, since we got all of our motors now, and they're all laid out in the shop, we can now accurately size these wires. And truth be told, we're really not going to focus on the controls part of it. We just don't have the time. But we are going to focus on these power wires. So when I say power circuit, talk about the wires feeding this actual motor. So from the MCC going out to the motor, we're going to size these wires here. That is what your power circuit wires are. And that's what I'm referring to when we say these power circuits. Also tied into that, in our bulletin book, I just have this here. If you want to reference it, you can. But y'all remember here a couple of weeks ago when we referenced this motor formula sheet pretty heavily, and we talked about all the steps, but we skipped a few, right? Well, if you look back through your notes, on step 3 here, that branch circuit wire size, we wrote skip for now, right? Well, this is these power circuits, that's step 3, branch circuit wires. So we're going from the MCC, so y'all remember what the definition of branch circuit is? Close. Not overload, but over. There you go. To what? Well, when we run a circuit, what are we serving? A what? A load, right? So if we look, the MCC houses all those buckets that we looked at where the fuse disconnect. So from our last overcurrent protection device out to the load. So this is a branch circuit, correct? So and it's part of the motor process. So today we're going to talk about this step 3. So if you open up your notebook and you kind of scroll through some of the tabs down here at the bottom, there will be a power circuit wire sizing cover page, and the page following that is the table that we are going to be utilizing. So, just to kind of briefly talk about this table and kind of introduce it, and then we'll kind of go into a couple of examples here. But very first column, of course, we have our machine ID. So if you notice in there, I filled in as an example M1-1. So you are going to have every single machine listed on here, right? Every single machine is going to have wires running to it from the MCC. So you can't just have M1 and then immediately go to M2, right? You have to have M1-1, M1-2, M1-3, M1- however many you got for each machine. So, truth be told, yes, you're going to have a lot. You're going to have probably at or a little more than 100 machines, right? That's for everybody. But every machine needs wires. The second column, the power circuit, That'll be probably one of the last things I show you, but just to give you a brief explanation on what that is, y'all remember whenever we did the receptacles, we put those tags in there and they said like RC and then a number? That's what that's referring to. We're gonna have something very similar to that for our power circuits. It's just a little tag, so that's all that's referring to. Then of course we have our our X, Y, rise and fall, those three distances, and then that's gonna give us our total length. One thing to note is our rise and fall does change, at least for these power circuits, but all of the rise and falls are going to be 50 foot for everything. So for the rise and fall stuff, we can at least kind of somewhat fill that out. But that will all be 50 foot. And just like the receptacles, it's going to be adding up your total length there. Then we kind of have some columns after that are talking about like largest FLA times 125%, some additional FLA columns, total amperage, and we really don't know what exactly to do with those columns yet. But then we got voltage drop. That's something, and that's more like a voltage drop permitted, and that's going to stay the same no matter what. So when we're talking about our motors over here, what voltage do they operate on? 480. So our motors are running at 480 volts. Now, is there any kind of transformer or anything on this line that I drew here between the MCC and the motor? No? So what voltage can we assume is on the MCC bus over here? Also 480, right? We have 480 volts being supplied throughout our shop. So for our voltage drop permitted, we're going to take the 480 we're going to multiply it, but what percentage does the code allow for voltage drops on a branch circuit? 3%. 5% is overall, system overall voltage drop. So when you first get from basically where your metering point is, all the way to the very last thing on your system, you can't lose more than 5. 3% is for branch circuits, so that leaves how many percent left for feeders? 2. So, but since we're doing a branch circuit here, we're going to take 480 volts, we're going to multiply that by 3%, because that's what the code tells us. And what number do y'all calculate there? Oh yeah, sorry, you'll need your calculator today too. 14.4. That sounds about right. 14.4 volts. So that's another column where we can have $14.4 all the way down. Like I said, that's really more like a voltage drop per minute. Then we'll have a CM calculated column, and then of course a wire size column on whatever wire size that you end up selecting. So at the moment, really just your machines, the rise and fall, and the 14.4 volts that we just calculated, that's really kind of the only thing that we could for sure kind of fill in. So that's where if we go look at this motor formula sheet again, it's going to reference us to 430.22. So let's go there. For me, that is on page 344. Page 344. Correct, 430.22. So before we read that actual code reference, if you kind of scroll up and you look there, we should be in part 2 of Article 430. What is the title of part 2? Very good. So does it specify if this is for branch or feeder circuits? No, right? So this is just kind of a general section. This is probably one of the few subsections of 430 where it's just kind of talking about everything. So if you got a motor hooked up on your circuit, doesn't matter if it's a branch or if it's a feeder, you're going to come here to size this wire. So we'll actually come back later on in the semester and come to the same section, same page, and we're just going to look at this for our feeder circuits. But right now, for our branch circuits, we can just look at this 430.22, and it's talking about a single motor. So kind of like this little example I drew over here, single motor. I'm rolling over here. Like maybe this is a M1-1. Let's just say it's 10 horsepower. But I'm going to talk about things like our M5 and our M6 here in a little bit. But right now we're just kind of focused on the machines that only have the one motor, single motor. But it states conductors that supply a single motor and used in a continuous duty application, which, reminder, all of ours are continuous duty, shall have an ampacity of not less than 125% of our motor FLA rating. So 430.22 is just going to tell us, hey, take your FLA, multiply that by 125%, and that's going to give you your required ampacity. So when we say ampacity, do y'all know what that means? It is, but what exactly is that talking about though? When I say this has to have this ampacity rating, what is that referring to? Not so much the heat, but what generates the heat? Current. The current, right? So when we say ampacity, all that's really just meaning to us as technicians is whatever number it is that we calculate right here, the wire has to be able to handle that many amps, right? That's what we're talking about when we say ampacity. But that's only about half the equation there. This wire has to be able to handle the amount of amps going there. And I kind of told y'all a little bit about this whenever we talked about our receptacles, but what's the other thing that we need to consider? Distance, which leads to what?
Wire size.
But ultimately, yes, but skipping a part in between. From here to here, what are we concerned about?
Loss.
What kind of loss? Voltage loss, right? Voltage drop. So we have to take ampacity and voltage drop. In my opinion, those are probably the two more important ones, right? There's other factors that go into it, but we're not going to do those in this project. But the distance between here, which ultimately leads to the voltage drop, is important, and that's going to give us those two comparisons. So the first thing we need to do is figure out our ampacity. So let's just kind of do this little M1 example I got here. So if we did this as an example, a 10 horsepower motor, that's going to have an FLA of 14 amps. I know that one off the top of my head. But if we take 14, and we multiply that by 125%, what do y'all come up with? What was it?
17.5.
17 and a half? Okay. So, for this example, that's what our wire is going to have to be rated to handle in terms of amps. Great. The second thing we have to look at, like I said, is that voltage drop. But we're going to do it a little bit differently than kind of how those receptacles work. So if we If you want to follow along, like I said, just scroll down a few pages in the bulletin book, but then there's this sheet, the voltage formula sheet. So if you notice there, the very top formula, that's the actual voltage drop. So if you wanted to calculate what your actual voltage drop would be in a situation, you use that formula. All these other formulas are just variations of that very first formula. They're just doing algebra to rework some of the variables in it. So we're going to end up using the one right below that, which is the wire size. So it says cm. But when we say cm, bless you, what is that? Do y'all know what cm is? What does that stand for? Circular mills. And then do y'all know what it is?
How big the wire is and how round it is.
Yeah, I'll take that. So the actual definition is if that was a piece of wire, if I just took a piece of wire and sheared it and we were looking at the end of the wire there, the circular mills, that's the cross-sectional area of that conductor. Not the insulation, but the actual conductor itself. So that's where a lot of all the wire sizes are derived of, and they all have circular mills values assigned to them. So we have circular mills is equal to, we're going to have to change this formula a little bit for our project specifically. But looking at the numerator there, the very first variable is 2. But that's only used for what kind of circuits? Single phase. Well, are our machines, are they single phase?
No.
No. So what do we have to change that 2 out with? There you go. Yeah, and it even says it on there too. That's all right. You can look at that. So you can do square root of 3, or its numerical equivalent of 1.732. It's the exact same thing. So we got that. And then it's times, and then that one is the only one that K variable is circled. So the K, that is talking about the exact resistance per circular mill foot. So on all the other formulas, you do solve for the exact K, but depending on whether you have copper or aluminum conductor, it's going to come out to about the same number every time. So for the wire size one, we're going to end up using a constant of 12.9, and that's just for copper. If we were using aluminum wire, I believe that value is 21.2. But that would be a constant. That 12.9 is not going to change. It's just like the square root of 3. You just have to have that in our formula. Then we have our distance, which that is going to be a true variable. That's going to be made up of our x plus the y distance plus the rise and fall. And then the last variable on the numerator is our load in terms of amperage. So that is actually going to be our required ampacity that we just calculated from 430.22. So this 17.5 amps here, that's what we're going to use in there. Not just 14, but we're going to put that 17.5 in.
So for the distance, it's basically just our total, our total distance, right?
Mm-hmm. Yep, that total length. Yep, and it'll auto load. All you have to, and I'll show you that at the end on how to get the distances on the drawing. But you're just going to get that X, Y, and of course the rise and fall is 50, and it'll add it up, and that will be your total distance. Now, one thing to note is even though we do have amperage in this formula, it doesn't consider that whenever it gives you a wire size. It's not factoring in amperage, right? So this is based all off of the voltage drop formula. So this is focused on voltage drop. Yes, even though amperage is a factor in there, it's not going to factor that necessarily into the wire size it gives us. So that's everything on our numerator, and everything is then going to be divided by voltage drop permitted, which we already solved for, and we said was 14.4 volts. So really it boils down to this formula. We only have 2 variables. One, our amperage here, that's really only like a variable of 12 max, right? Because we're all going to have, like for example, if you got multiple M1s, Well, the motor size isn't changing, right? It's gonna draw the same amount of current, but no matter if it's M1-1 or M1-2, it's drawing the same amount of current, right? What's changing is the distance. So you'll only have a maximum of 12 variables here for your amperage, and distance, that's really the only variable that's gonna change every time. So really you got kind of 1.5 variables to change out in that formula, and it's gonna be on repeat. So if we kind of continue our example here, and we kind of plug in our values now with our formula that we have modified for our project. So we'll say square root of 3 times 12.9. And I'm just going to make up a distance for example reasons, but let's just say it's 100 foot between the rise and fall and the X and Y. Let's just say we had 100 foot on the dot. But 100 foot times, we calculated 17.5 amps. That's our required ampacity. So we'll plug that in, and all that's going to be divided by 14.4 volts. So don't forget to put parentheses on your numerator, but go ahead and punch that in your calculator. Let me know what you get. So what, just 2.7K?
2,715.
So like 2.715, okay?
Yeah.
And that's K what? K circular mils. So that's our circular mils that we just calculated. Did everybody else get the same number? So this is so whenever we do these calculations, this is a great time for you to punch it in on your calculator. It shouldn't just be one person doing it. Because guess what? If you're not doing it here in class and getting the same numbers, well, whenever you go do it on your own, you start punching stuff in, you think it's right, but you punched it in wrong, then, well, now you did all your math wrong. So this is a great time to kind of verify, make sure everybody's getting the same values. So that sounds right to me. But is that really kind of any tangible information that we can utilize? Does that mean anything to us? Like if we walked into Home Depot and said, I need some 2.715 thousand circular mil wire, do you think they're going to know instantly what we're talking about? No, so that's not a tangible wire size for us. So for us to kind of translate that, if you will, to a wire size, we're going to have to flip all the way to the back of the book, pretty much all the way to the back of the book, to table 8. And that's on page 725. So if we're looking at table 8 here, and of course, on the very far left-hand side, we have our size of our wire. The second column is our area, and then that splits into 2 subcolumns. We got millimeters squared, which nobody cares about, and then we have circular mils. So we need something that is equal to or greater than what we just calculated here of 2.715. So what wire size does that come out to? 14. A number 14. I would agree with that, right? So that's equal to or greater than what we just calculated. Now, this is a pretty common instance, but what is the smallest wire size available for us to use in our project? 12, right? So with that project constraint on there, can we really use that 14 gauge wire? No. So if you have something like this, where you calculate a small 1,000 circular mils, 2,700 circular mils, something like that, and it gives you something less than a number 12, that's okay, but it automatically kind of gets bumped up to a number 12 because of our project constraint of that being the smallest wire size for us to use. So even though, yes, the calculation does come out to a number 14, we're just going to go ahead and bump that up to a number 12. So we're going to say table 8 gives us a number 12. But do we know with 100% certainty that a number 12 conductor can handle 17.5 amps? So how can we look that up? Y'all remember the table for that? So we're going to go to table 310.16. That is on page 187. Page 187. And if we look at table 310.16, excuse me, let's talk about ampacities of insulated conductors. Ampacities, right? We kind of talked about that already. So, how much current these wires can handle. So you all remember the type of insulation that we're using? Well, it's a copper conductor, but what type of insulation are we using? Yes, THHN. So that falls underneath what degree column there? 90 degrees. So make sure you are looking on the left-hand side for copper, but look at the 90-degree column and cross-reference that with the number 12, and what value does it tell you there? Do what? 30. So, can this number 12 be used for this example M1 that we're doing here? Yes, all day, every day. So in this example, we would end up using that number 12.
And what are you comparing that 30 amps to?
I'm sorry?
What are you comparing that 30 amps to?
So, whatever wire size table 8 gives us here, so like I said, we went to table 8, it really kind of gave us a 14 based off of the circular mills we calculated, but we kind of bumped it up to that number 12 just because of our project constraint of, hey, that's the smallest wire size we're going to use. So all we did is we went there to table 310.16 to verify, hey, this number 12, can it handle at least 17.5 amps, what we calculated for our required ampacity. So whenever we do our circular mill calculation, it's not always going to have that factored in there. So say for example, table 8, we got a number 12 still, but instead of 17.5 amps, we had 50 amps, right? Well, we'd come over here to table 310.16, we'd say, oh, well, number 12 is only good for 30 amps. I can't use that. Well, that's okay. Then you would just bump up to the wire size that can, which looking there would be like a number 8. So you can always size up from table 8 whenever you come over here to look at 310.16 for ampacity reasons, but kind of this workflow of going forward, never work backwards. Never work backwards. So what I mean by that is if table 8 gives you a number 8 wire, right, and let's just say we're back at 17.5 amps, but say table 8 calculation gives you a number 8, you come over here to table 310.16, you're like, oh, number 8 is good for 55 amps. Well, I only need 17.5. Let me size it down. No, that's not how that works, right? You don't work backwards. Whatever table 8 gives you for its wire size, that's the smallest wire size you can use, minimum. And you might have to increase that due to amperage reasons. So when we do this process right here, you're taking your ampacity and your voltage drop and you're kind of comparing them. So we start out with the voltage drop, and then we verify that that wire size can handle the amperage. And if it can, great. If not, then you size up the wire so it can handle the amperage, right? And the reason we're kind of protected doing it this way, kind of this flow of things with doing the circular mills, then table 8, then verifying the ampacity, is if we increase wire size, what happens to its resistance? It decreases, right? So to prove that to you, if you don't believe me, let's flip back to table 8, page 725. Let's flip back there for just a second. But on table 8, if you kind of go on the right-hand side of the table now, you'll see where it says copper up there, and then it'll have below that uncoated or coated. Let's just look at uncoated, and then you should see ohms per kilofoot underneath that. So starting out with the number 18 gauge, solid number 18, what is its ohmic value there? Copper uncoated, ohms per kilofoot. So almost 8 ohms. Okay, so what that means is if I had a spool of number 18 solid conductor, and I had exactly 1,000 foot of it, and I took my multimeter and I measured both ends of that wire, I should measure 7.7 ohms. Okay, so now looking down that list of where 7.7 ohms is, if you kind of go down, so as you're going down, our wire size is increasing, but what do you see what's happening to the ohmic value? It's going down, it's decreasing significantly, right? Those smaller conductors really have a higher ohmic value. So the way I kind of like to think about it is if it was a perfect world. But say your wire size, that's kind of like I-35. Well, if you have a number 18 gauge wire, that would be like if it was just a 2-lane highway, right? Everywhere. There would be traffic galore on there, right? Between you and all the semis and everybody else on the road, right? Well, as you increase wire size, it's like adding more lanes to the road, right? So like I said, theoretically, in a perfect world, if you had 36 lanes going northbound or southbound, there'd supposedly be no traffic, right? But, yeah, exactly, right. Like I said, that's why I said perfect world. But theoretically, kind of going along with that little analogy, if you have more lanes, you should have less traffic or less resistance on the road, right? So, like I said, if table 8 gives you a wire size, that's only good for the voltage drop. It's just, table 8 is just saying, hey, between here to here, if you put this wire in, you're not going to lose more than 14.4 volts. That's all table 8 is telling us. So it's like, okay, good, that's kind of our bare minimum. The second half of the equation is okay, well, this guy right here, depending on how much current he draws, can that wire handle it? And that's what table 310.16 is for. So we check that. And if it can handle it, great. If not, then you increase the wire size. And if you increase that wire size, you add more lanes to those roads, you don't have to worry about voltage drop because you already know it's good.
I have a question.
Yeah.
On the table that we just referenced, there's a quantity of 1 and a quantity of 7. Are we going to use that quantity of 7 at all?
So what that's referring to on table 8 is between your solid or stranded conductors. So if you'll notice there, the first several wire sizes, they're kind of smaller in retrospect to everything, and they do have quantities of 1, so you can get solid conductors up until that number 6 wire there, and then everything from that pretty much transitions to strand.
Okay, thank you.
But for us, we are going to run stranded for everything. Not that that really makes a difference for anything that we're doing this week, because if you go to table 310.16, it doesn't care if it's stranded or solid conductor. If you have a wire size in that smaller kind of area, it doesn't care if it's stranded
So we're
or.
going to use the number on the bottom in that case, right?
In which case?
Well, because you said the numbers, you said it's going to be the 7 for stranded.
Mhm.
So, and then, like, if we were to do the 18 wire, it would be 7.95 for stranded.
Right, for the ohmic value.
Okay.
Right. But we're not actually going to use that in any of these calculations this week.
Okay.
Yeah. And if you really wanted to, you could, like, if you look at the receptacle stuff, actually, I'll just pull that up. So, even from whenever we did, like, our receptacles there in the office, if we look at the ohmic value, number 12, 1.98. Okay. Well, if we look here, 12, solid, it's, whoops. It's ohms, copper uncoated ohms per kilofoot is, for a solid, is 1.93. But then if you go to stranded, it's 1.98. So just by looking at that, you already know that all these wire sizes, or at least at number 12, but all of them are, they're all technically stranded conductors, not solid conductors, right? But like I said, that's really not going to affect it. We're not really utilizing it. I just wanted to show you that resistance on there to kind of prove that as you increase wire size, your resistance is decreasing. Yep, good question. But does anybody have any questions over the math for the single machine over here?
We're using that same voltage drop permitted formula for all of our calculations.
Yeah, the voltage drop permitted, that's going to be the same for everything. But from these first two steps that we did right here, this is just for a single machine.
What about the additional FLA?
We're going to talk about those here in a second. Yeah, I'm about to fill all this in on the chart up there, but I just want to make sure that everybody's good with this process. Like I said, kind of mostly understands getting your circular mills, then table 8, then 310.16. Like that's the flow it should go. It should never go backwards on any of that flow. But everybody's good with that math? Yeah.
For
The what? Uh-huh. Yes, I'm going to show you all that at the end. That and the power circuit tags, I'm going to show you all that at the end. All the drawing stuff, I'm going to show you at the end. Yep. But everybody's good with the calculation. Okay. So, as far as on our notebook here, go back to that page. So what we're going to do to fill this in, of course, like I said, I'm going to show you at the end how to get these distances for real. But after our total length, this is kind of set up to kind of follow your steps here. So step 1 was we had our largest FLA. Well, if we only got one motor on a machine, that motor's FLA is kind of just the largest. So in this example, we had that 14 amps on that 10 horsepower motor. So that's my largest FLA. Then we have step 1, 430.22, taking our largest FLA times 125%. Well, that's our step 1. So we calculated 17.5. So I would fill that in. Additional FLA. We didn't have any other motors on that circuit. So I'm just going to fill in NA. We don't want to leave them blank. If you leave them blank, it's kind of understood that that's not been calculated yet. So we don't want to have that kind of thought go through. So we want to say, nope, that's not applicable to us here. And our total amperage, that's basically the required ampacity there. So what is our required ampacity that we plugged into that step 2, our circular mills formula? Well, since it was only just that one motor, that was 17.5. Voltage drop, that's already the same. The circular mills calculated, we had gotten 2.715 thousand circular mills. And then our wire size, we ended up selecting a number 12. So that's kind of how you would fill in that information. Now, you might have like a scrap piece of paper that you write those steps right there that I just did with y'all on there, and that's fine. But this page right here, this is the only page that you have to show your work. Like this page right here is showing all of your work. There's not another page or anything to fill out. So if you fill out this table here, then you're good. You're showing your work, right? But you do have to have this page filled out. Like I said, if you got a scrap piece of paper showing or jotting down your notes and formulas and stuff, that's fine. But this page right here is sufficient enough to show your work. So everybody's good with taking this calculation and kind of transferring it to this table? So that's probably about 95% of what you'll do this week, is for our single motor machines. But we do need to talk about our multiple motor machines, which are our M5 and our M6. So they are not going to follow this same code reference because 430.22 is for a single motor. So again, if I kind of draw a little example here, here's my feeder, here's my set of fuses. Instead of one motor, I now have, and I'm going to do an M5 example, just because it's quote unquote more complicated. Well, let's just say there's an M5, right? Well, that is no longer a single motor. So, we're going to have to follow a different set of rules. Not that different. But let's turn back to page 344. And instead of looking at 430.22, we're now going to look at 430.24.
About 24.
430.24. So if we look at the title of that one, it now says several motors or a motor and other loads. Well, is that an accurate description of what our M5 is? For the little one line I drew up there. Yes, I would agree. We have several motors here. So it states conductors supplying several motors or a motors and other loads shall have an ampacity of not less than the sum of the following. So kind of keep that in mind, not less than the sum of the following. So we're going to have to add these steps up here at the end. But it says step 1, 125% of the FLA rating of our highest rated motor. So step 1 here is our largest FLA times 125%. Well, that sounds pretty similar to what we just looked at, 430.22. So this little example that I got going on over here for my M5, I just have all three motors as a 10 horsepower motor. So you might have all three of your motors the same size, or maybe 2 out of the 3 are the same size, doesn't matter, but you might have this situation, but which one's technically my largest? Any of them, right? Because they're all the same size. So, like I said, if you kind of fall in that same category, you would just pick one. So, I'm just going to say, you know what? This one right here, that one's going to be my largest. So, same process. So, since these are all the same amperage, and thankfully we did that calculation already, but we'll say 14 amps times 125%. We know that that gives us 17.5 amps. Like I said, this one was kind of tied to step 1 here. Okay, that's pretty on par with everything we've done so far. So let's look at step 2. It says the sum of the FLA ratings of all your other motors in the group. So it's basically saying for step 2, let me write that out first. But the code is basically saying, hey, for this piece of wire that you're going to be sizing here for this M5, these 2 other motors, they're still going to draw current, right? So we have to factor that into for what this wire size can handle right here. So these 2 are going to be tied in with step 2. And since they're all the same size motor, we already know the FLAs of these are 14. So we're going to say, okay, well 14 amps plus 14 amps, that's going to give us 28 amps. Okay, makes sense. And then step 3, it's talking about non-motor loads. Well, we already kind of looked at all of our motor loads, but do we have any non-motor loads up here? No, right? We don't have any kind of lights or anything else that this M5 is talking about. So really the step 3 here, that's in A. And if we look at step 4, it's also talking about non-motor load stuff. Well, we don't have any non-motor load stuff, so step 4 would be not applicable for us. So really we're just doing half of this code reference because that's all that's applicable. So keep in mind, when we first read this deal, it said we needed to take the sum of these steps. So really we're going to add together steps 1 and steps 2. So that's going to be where we take 17.5 amps plus that 28 amps. And what does that come out to? Thank you. 45.5 amps. So that is now going to be whatever that total is for you. But for this example, that 45.5 amps, that is now going to be our required ampacity. So really that step 1 there kind of changes just a little bit, because we do have to factor in these 2 other motors here on this machine that are going to be drawing current. After that, guess what? We got the same step number 2 over here. It's still going to be using that circular Mills formula. So if we kind of plug in all our variables here, circular Mills is equal to square root of 3 times 12.9. I'll just say we still got 100 foot of distance total, just for simplicity. Let's just say we got 100 foot distance, but now my required ampacity is this 45.5 amps. So that's what I'm going to end up using in this formula. So 45.5 amps, all divided by at 14.4 volts. Again, don't forget parentheses up here on the top. When you do that calculation, what do y'all come up with?
$7,059.
So 7.059? 7.059 thousand circular mills. Well, guess what? It's the same process. So we're going to take this number, we're going to go to table 8. It's going to give us a wire size. So let's go translate that. So if we flip back to table 8, page 725, we need something that is equal to or greater than, just barely, a little over 7,000 circular mills. And what wire size does that come out to? What was it? 10. I would agree with that. So table 8 tells us number 10 conductor. But do we know for certain that a number 10 can handle 45.5 amps? Exactly. You have to go back and you have to cross-reference and verify there. So now we're going to head over back to table 310.16. We're going to verify to see if this number 10 can handle 45.5 amps. So flip back to page 187 there. Where the tabs kind of come in handy. But flip back to page 187, table 310.16. how many amps can number 10 handle? So number 10 is only good for 40 amps. Can we use it? No. So this is a great example of where table 8 gave you the minimum wire size based on voltage drop. So between these 2 points here, it said, hey, if you use the number 10 wire, you ain't gonna lose more than 14.4 volts. Great. Now the issue is this, really it's these motors, because it's an M5, but these 3 motors over here are gonna draw more current on this line than what it's rated for. So we have to increase the wire size. So go ahead and pick a wire size that can handle 45.5 amps at least. And what wire size do y'all come up with?
8.
And number 8, how much is that good for?
55.
55. So in this case, we would end up picking that number 8 conductor. It's almost the exact same process. You just have to factor in those other 2 motors. M6 is the exact same process. It's just this step 2 here for 430.24. Instead of having 2 extra motors, you only just have that 1 extra motor, right? I just do the M5s because they're more complicated. So does anybody have any questions over the math for the multi-motors? I said almost the same process, just a little bit different. So, as far as our spreadsheet goes, I'm going to skip a few lines here, but let's just say this is our M5-1 example here. But our largest FLA, again, kind of following the first steps here. Well, we have multiple motors now. Mine just happened to all be the same size in this example, but largest FLA, that was still 14 amps. Well, sub-step 1 there, largest FLA times 125%, that was 17.5 amps. This is now where we use the additional FLA columns. So your M5 will utilize both of them. The M6 is only going to utilize 1. So on the M6, you'll have one of those additional FLA columns marked as NA. But here, this is where we're going to punch in those extra 14 amps. This is kind of that sub-step 2 there. And our total amperage, well, that's kind of where we added everything up together down here to get that 45.5. So we're taking the largest FLA times 125% plus that step 2 of 14 plus 14, which was 28, which in total gave us that 45.5. Circular mills calculated, 7.059 thousand, and we ended up with a number 8 conductor. So, oh, yeah.
Since we're using the same voltage, that's just gonna be a constant?
Yes, the 14.4 will be all the way down. Yep, that's going to be used all the time. Like I said, this is more like a voltage drop per minute is really what this is. It's really what that is. Not necessarily true voltage drop, that's more like I said, the voltage drop per minute. So meaning that's between that MCC and that machine, that's the maximum amount of volts that you can lose between those 2 points. Is there any questions on how to take the math for the multi-motors and transfer it onto the table here? So everybody's good on how to size the wire for your machines, power circuit wires? Okay, so the last little bit with this deals with the drawing, because that's kind of this information over here that we didn't fill out. So, in the shop drawing, so if you open up your shop, of course your shop should be, from last week, should be all filled out, right? I just kind of mocked up this little corner over here. to kind of give us a little example here to work with. But first thing we're going to do is we're going to draw in all these little tags, or we're going to draw in the actual power circuits. So when I'm working on this, okay, I don't want to have every single layer turned on if I don't need it. So for example, like these machine work zones, I definitely needed that so I could lay out everything in my shop. But when I'm talking about power circuits, I don't need my work zone layer on. So I'm just going to come up here to the layers and hit the little light bulb on it and turn that layer off, just to kind of help clean up some of the clutter. But if you go back to the layer drop down, you'll notice kind of right below that work zone that you have three blue layers, light blue layers. And they're called power circuit dash line, power circuit home run, and power circuits. I really don't know why there's three of them. We don't really need three of them. But I'm going to go on the power circuit home run layer. That's where we're going to start. And very similar to receptacles, but if you come up here to insert block, you'll see that there's a power circuit block. And it looks almost identical to the tags that we used for receptacles, except now it's blue and it says PC for power circuit. It even has the same tag number or placeholder of 77. So we're going to take that. Now, you can kind of put this tag kind of anywhere around the machine, but just keep in mind, just like receptacles, this is going to have an arrow tied to it. So for me, since my MCC is right over here, I probably don't want to put this tag on the back side of my machine, because then you're going to have arrows and tags and everything overlapping, and that affects neatness, right? So I'll just put my tag right there, for example. Just like receptacles, the attribute box is going to pop up. Again, that 77, it's just a placeholder value. So since this is my first power circuit, I'm going to start with circuit 1, right? Very similar, the next thing I'm going to do is go back, get me my power arrow. It's set up the same way as the receptacle, so it's offset from your cursor. So that way all you have to do is just kind of hover over that center point of the tag, and it'll line up the edge of the arrow with the edge of the tag perfectly. Put it down, and then guess what? You're going to rotate the arrow back to where it's fed from. So for me, in this example, it's fed out of this MCC1, so that's where I'm going to point it to. The last detail is we're going to switch layers to that dashed line, power circuit dashed line. Use that spline command again. And we're just going to tie our machine to that tag. Like so. So kind of once you get one in, you can kind of just mass copy them exactly. Put them all on the same side if you really want to. You can put them on different sides, I don't care. But then you can come in here. Of course, you will have to change the value on the tag. So these would be like 1, 2, 3, 4. But that's a heck of a lot easier than redrawing every single one. And like I said, I'm doing these 6 here in probably less than a minute, like so. And then of course you will also have to put all the arrows in, but like I said, there's even putting the arrows in don't take too terribly long.
And you can just do it to the center of MCC1, but
Yep.
it'll be like 1.
No, just as long as it's pointing back to the MCC. So like I said, in a matter of what, a minute and a half probably, I put in 6 tags, just like that. So change the numbers, put in the arrows, done. So it doesn't take too terribly long. So the biggest thing is like I said, just don't have any of your machine and your tags and arrows and stuff overlapping. Just keep it neat, right? So like mine, it's got good spacing, nothing's overlapping each other, it's nice and neat. So does anybody have any questions on how to draw the tags in? Okay. So these tags, as far as how that is referenced back to our spreadsheet, that's what's filled in on the power circuit number column here. So if we look at the drawing, this M1-1 here,
Well, that was my very first power circuit. So as far as the spreadsheet goes, I put in circuit 1. For my little M5 example, notice I did change one of my machines to say M5-1, but that's tied to tag number 6, right here. So when I come back to my spreadsheet, I would put 6 right here for my power circuit number, right? So your tag and your machine ID need to match on this spreadsheet. So realistically, you'll probably start this week out by putting in all the tags, so that way you know what tag is on what machine, right? So, as like I said, as long as the tag number matches the machine ID on the drawing and on the spreadsheet, you're good. So everybody's good with that? Okay. So the second thing we need to get off the drawing, which again is probably kind of the second thing you'll do for this week, but that is getting our X and Y distance. So just like the receptacles, we're going to use that dist command again. Now, as far as where you want to point and click, I mean, you're splitting hairs, but for me, I always just kind of go on this back side of the machine at the midpoint, just because it's an easy snap. But I usually just click there, and then kind of go back to the MCC. Just like the receptacles, it's going to give you your X and Y distances down here at the bottom. And just like receptacles, I would do the same thing as far as like rounding up. So like for example, on this one here, my X measurement was 10 foot, 5 5/8 of an inch. Call that 11 foot, right? I wouldn't spend the time worrying about the inches, just round it up to the next foot on all of them. So like I said, I would round up to 11 there on the X. My Y, same thing, it says 12 foot, 5 3/16 of an inch, call that 13 foot. So I would take 11 and 13 and plug it in. Of course, we got a rise and fall of 50. Wasn't too far off, but I know in my examples up here I just made up 100 foot, but if we were to redo this example, that 74, that would go right here in place of that 100 foot or whatever value you calculate there. Like I said, I just made up these 100 foots for example, but that's how you get your actual distance. Yeah.
You said that you want to go from the middle of the piece, or I guess the home run, right?
Well, I don't go off the home run, I go off the machine.
Oh, yeah.
But where you click on the machine and where you click on the MCC, you're kind of splitting hairs. Me, I just go off of the midpoint on the back side of the machine, from there to the middle of the MCC. That's just where I click, but like I said, you're really splitting hairs on where you click.
So even if it's just a half inch over 10 foot, just go ahead and call
11.
it up.
Yep. Yeah, I don't know how much electrical work y'all done, but and one thing that really gets my blood boiling is when I'm working, especially in a house, you got about that much length of wire sticking out of the box. Yeah, that'll make a bad day real quick. So, in my opinion, it's always good to have some extra wire in there, right? That's always a benefit to you. So it's always the little things that get you on the job. But yeah, I would always round up, even if it is like a half inch over, round